So what about even bigger stars? So, sort of bigger than 1.3 solar masses, so 1.3 times the size of our sun. We have this thing called the CNO cycle. So this is a cycle because it goes around in a circle. You'll see in a second. Our sun does a little bit of this, so some of its energy is actually produced through the CNO cycle. And as you'll see, one cycle of this also produces 26.72 mega electron volts. So it's like a different process for the same amount of energy. Right, so this is the main fusion reaction in like really hot, really giant stars. And the reason for that, the reason why it's not in the smaller stars is that this reaction requires a much higher ignition temperature. So you just can't get the heat in smaller stars. You need those really massive stars for this to occur. So in this, we've got carbon acting as a catalyst. And you should remember from year 10 chemistry, or if you're doing chemistry now, a catalyst is something that can speed up a reaction, it can enhance a reaction, but it doesn't get used up in the process. So without it, the reaction might occur, but it'll be slower. The catalyst helps it along, but it remains unchanged. Like it can change during the reaction, but at the end of the reaction, it has to be back to how it was. So carbon acts as a catalyst, and it's basically converted to nitrogen, and then it's converted to oxygen, then it's converted back to carbon. And while it does that, it actually produces 4 protons and 1 helium-4 molecule. So one of those heliums that has the 2 protons and the 2 neutrons. Okay, so let's go through step by step. And I'll put myself Brady Bunch in the center of the carbon, nitrogen, oxygen cycle here. So let's have a look around it. Okay, so can you find in there, or if you're more of a somebody who likes words, then you can just have a look at the actual equation, and that's just okay. Either way, whatever suits you. So we're going to have a look for our carbon 12. Okay, so carbon 12 is going to have 6 protons and 6 neutrons. So here's our catalyst. It's going to start the entire thing off, and you'll see in the last column the last row of the equations that there's also a carbon 12, and that's why, look, we start off with carbon, we end off with carbon. No carbon is used up in this process. Is it the same carbon molecule that started and finished? Not really. But it's not used up, so therefore we say it's a catalyst. Okay, so we've got our carbon 12, and remember we're in the middle of this really incredibly hot plasma ball. So there's lots of hydrogen flying around, and we get a hydrogen, just a single proton, like a hydrogen nuclei, slamming into the carbon 12, and that forms a nitrogen molecule. Okay, so basically you've ended up with 7 protons and 6 neutrons. And that releases a gamma ray. So we've got some energy, yay. Okay, and that's going to make its way out of that supergiant star as radiation. Okay, so that nitrogen then breaks down to, because it's not stable, it breaks down to carbon 13. So basically it chucks out a positron and it chucks out a neutrino. Right? Okay, so what's happened there? Well, basically a proton has turned into a neutron. So just like we saw in the proton-proton chain, but in this one, basically the proton inside that nucleus has converted to a neutron, and now you've got a positron, and a neutrino getting chucked out, just like you had a positron and a neutrino being produced in that other reaction. Okay, so now we take our carbon 13, which has 6 protons and 7 neutrons, and we slam another proton into it, so another hydrogen nuclei. And that's now going to slam back into it, and what do we get again? Oh, we get nitrogen again. So, but this time, okay, it's like a 14, an atomic mass of 14, so it's got 7 protons and 7 neutrons. And this produces another gamma ray. Yay, so we've got some more gamma radiation being produced to power this star. Okay, so we've got our normal nitrogen nuclei now, and we throw another proton onto it. So we just slam another one into it, and when we do that, we increase the atomic number and the atomic mass by 1, so we get oxygen. So now we've got oxygen with 15, a total of 15 protons and neutrons together. So basically it's going to have 8 protons and 7 neutrons. And that's going to produce another gamma ray. So we've got more energy coming out. Okay, so then we take that oxygen with 15, and it does that kind of thing again like the nitrogen did earlier, and it converts a proton to a neutron. And that's why it drops down to nitrogen, because now it's only got 7 protons, not 8. So therefore it's nitrogen, and it chucks off a positron, and it chucks off a neutrino. And then that nitrogen 15, another hydrogen nuclei, another proton slams into it, and we end up with, it just goes, it's all too much, and it breaks apart into a carbon 12, which is what we started with, and a helium nuclei, or helium, which is really cool. So we've got our helium. So you can see, follow around the picture, and you can see that happening. Each of those little star things is like that saying there's an explosion there. That's all, or like, not an explosion, but that's where they're slamming together. Anyway, try to pull that apart, because you're going to have some questions on that soon.